Okay, so now that we finally figured out the escape velocity from Earth, we can finally play around with a black hole.
Awesome.
So we made it to the black hole part. So in our code, what we're going to want to do is replace where it says draw planet with draw black hole, and we will have a black hole drawn. So what I'm going to do is copy this piece of code to the clipboard, go back to my code, and at the very bottom, it's where it says add more graphics here before the end of draw, open and close parentheses. I'm going to delete draw planet, and I'm going to put click Control V to paste draw black hole. Yeah, so with this, we will have a black hole in our code now. I guess we could quickly see that. So yes, there is our small black hole. And we can see that with everything we have right now, it's escaping just like it did with the planet, because we haven't changed anything else. All we did is, instead of drawing an Earth, we're drawing a black hole.
So empirically, we found a couple steps ago that the escape velocity looked to be about 65. And we also went to the board and we discovered that it was actually 63.25. Now we want to get a little bit more physical and incorporate some relativity, which is the idea that nothing is allowed to move faster than the speed of light. So we're going to do this by going ahead and saying that we're going to have some speed of light that we denote by c, and for our purposes we'll set c equal to 50. And we're going to add that to our code near the beginning.
Right. So we're going to copy this again, copy to clipboard, go into our code, and we're going to put c right above where we define what our velocities are, and I'm going to paste it using Control V again.
Okay. And in order to make c a meaningful limit, we're going to also incorporate some if statements. Now what an if statement does is it tells your computer when it's reading the code, if a certain condition is met, then I want the computer to respond in a certain way. Since we always want our velocity to be at most c, we're going to use 4 separate if statements that takes velocities that are larger than c and brings them and makes them smaller. So for example, in this first line here, you can see that if Vx is greater than c, then we're going to set Vx equals to c. And similarly, if Vx is smaller than negative c, then we're going to reassign Vx to the value of negative c. And we keep doing these same steps all throughout for y as well. So if we copy those into the clipboard, we want to paste them. We're going to paste them in our draw function, because remember, at every step of this code, the computer's running and it's recalculating your positions and it's your velocities. And we need to check this at every single one of those steps. So Danielle is going to paste it. Okay, thank you.
Right there.
Right here. And we can give it a test if you like.
So, yes, let's give it a test.
Okay. Okay. And we see now we started at some position that was pretty close to the black hole, and now we're caught up in a bounded, closed elliptical orbit.
So there's also one thing we need to do. So after setting this to c, it's important to also set this Vy equals to c. So that way we know for sure that we're not going to, any number that we put there, it's not going to exceed the speed of light. So now if we quickly run this, and if I were to draw a velocity vector, say I want to start launching from out here, seems like I am
Got far out of there.
Gonna get far out of there. Yep. Right. So now, just to see what happens, let's see if I start, what's going to happen if I use that same velocity vector but start closer to the black hole. Oh. Seems like I die immediately. Let's try that again, but with a different velocity vector. Say I want to start, make it go out here. So this seems like I keep dying the closer I am to the black hole, but when I'm out here, it seems like I can pretty much escape it. So it seems like there is a relationship between, there's a relationship
that exists when we have to consider whether we need a certain velocity to escape and where we have to be to escape. So if we're far enough away, I think we should be able to, if we're far enough away from the center of the black hole, we should be able to escape with, a bit less of a velocity. And if we get close enough to a black hole, it doesn't matter what velocity we pass this, because of our if statements limiting them to c, that we're just going to crash eventually. So, since light cannot escape, and one of the things we know about light is that light is is made up of massless particles called photons, we can try changing the mass of our object and see whether something like light should be able to escape. So if we scroll down in our code a few lines, there's a point where we have to define some accelerations here. And the acceleration, from Newton's equation, we know that force is equal to the mass times the acceleration. So simply rearranging that equation will tell you that the acceleration is equal to force divided by the mass. So here, around this part of the code, we have some delta Vx's and delta Vy's defined by F of the force you're applying divided by the mass of our object times some change in time, which is, in other words, the acceleration times the change in time, which is a velocity. However, your computer does not understand and doesn't like to work with divide by zero, as we're not really allowed to do that. So you would have a problem trying to actually run this code if we divide it by zero.
So let's just make sure that it indeed does fail with a mass of 0. Let's shoot it out. Oh, doesn't even want to.
It doesn't want to exist. We can't calculate any orbits for this object at mass 0 because we can't get any accelerations for the mass 0 object. Now, for particular coding reasons, such as dividing by 0 errors, we're not going to go set the mass exactly equal to 0, but we can get reasonably close to 0. So the mass that we start with in the code is about 3 in our choice of units. So we can try again with something like, say, 1.
All right, so we would go up here to our code, and right here where it says mass, we're going to change this to 1.
And now we're going to try and launch again under similar conditions as before.
So we're going to try 2 different launches. Again, one that's far away from the black hole and one that's sort of close to it. So my first launch far away, be like right there. Seems like I'm escaping it.
Yeah.
And if I try again, but close to the black hole.
Let's see. Oh, we die again.
Die again.
The results look the same to me.
Yeah. How about we try an even smaller number?
Is half big enough?
Yeah, let's try that one out.
Okay.
So let's do 0.5 and see what results we get. So again, I'm going to start out here and give it some velocity, and it seems like it's escaping.
We're out again.
It's fine, yeah. And now let's try closer to the black hole with that same velocity.
Wow.
Wow.
That was interesting.
That was interesting.
So it spiraled a bit more.
Right. But in the end, you still
crashed.
You still crashed it.
Okay. Let's go to something unimaginably small. What's the smallest number you can think of?
Without it being 0, how about we pick 0001?
Okay.
Right.
Let's see.
Let's try this
If this doesn't do it, I don't know what will. All right.
Wow, we're still escaping.
Okay.
So far away from the black hole, we're still escaping, and then close to the black hole.
Do we escape?
Do we escape?
Let's see.
It looked promising.
Are we going to be in some kind of orbit now?
It's coming right back. Uh-oh.
What should survive?
Yeah, that one should survive.
It's not escaping, yes. We're in an orbit. We didn't escape. So even light is stuck. And if we waited long enough, it could very well just crash. Wow. So this doesn't depend on the mass at all.
Yeah. So, again, we saw that the further away you are from the black hole, you manage to escape. Whereas the closer you are to it, you either are bound to it or you just crash inside toward it. So we want to know what this radius is. How far from the black hole do you have to be in order to either escape it or stay bound to it?